Okay, so we've already talked about accuracy and precision in this unit when talking about measurement. Remember, accuracy reflects or is how close we are to the true measurement of something, and precision means if we measured over and over, would our results be very close to each other? If they are, it's precise. If they're not, it's imprecise. Okay. So now we're going to talk about uncertainty, because basically, I mean, no measuring device can be perfectly accurate. Some can be better than others. Okay. But you know, like a ruler, a standard ruler can be somewhat accurate and precise. If it's broke, the more notches it's broken down into, but it can't be absolutely perfect. So there's always going to be some uncertainty, and we reflect that when we measure things. So normally when you guys have measured things up to this point, you've just written a number, a value. Okay? But we want to account for that it's not quite perfect. It could be a little more, it could be a little less. Okay? And so to do that, we write something in terms of uncertainty. And how we write it, a general sort of formula, I guess, is whatever the measured value is, which you guys are used to doing, plus or minus the uncertainty of the measurement. So how do we find the uncertainty of a measurement? Well, it depends, okay? So if you look at this example here, we've got two figures that we're measuring the same object. It's just that figure B is more blown up than figure A, okay? So figure B would be a little bit easier to read than figure A, okay? Because if you looked at figure A, you'd say, okay, if it's broken up into tenths, so this is 1 centimeter, which means each of these notches is a millimeter. Looks like it's a little bit more than 9 millimeters. Kind of hard to see exactly how much. Maybe 0.2, who knows? But if it's blown up, it is a little bit easier to see. So we can see that we're maybe 9.3. But how we calculate it using uncertainty is we write down what we think the measured value is, and then we account for the uncertainty. It could be a little bit more than that. It could be a little bit less than that. So how do you calculate the uncertainty? Well, whatever you do, so let's say we're going to the nearest millimeter for this one, not centimeters. We're going to the nearest millimeter. So we could say maybe 9.3. Okay? 9.3 millimeters. The uncertainty, how we calculate the uncertainty is we would take the precision that we're measuring to. So it would be the nearest tenth of a millimeter, right? We learned that last lesson. It would be the nearest tenth. So what you do is you take 0.10 and divide by 2. Because half of it's going to go above, half of it's going to go below. That's why we divide by 2. So we get 0.05. That's going to be the uncertainty in millimeters, which means how we would write our final answer is 9.3 plus or minus 0.05 millimeters. Notice here I did it in the paragraph here, it says it in centimeters, but I did it in millimeters because it's a little bit easier to see. So what that means is, yes, we're measuring to the nearest tenth of a millimeter, but we could be 0.05, the actual measurement could be a little bit above, or could be a little bit below that. So that's really the biggest part of this lesson, is how to calculate uncertainty. You take whatever it's precise to, divide by 2, and then that's your plus minus. So uncertainty is related to precision. So for example, if we go back to this, we could look at this in millimeters like we did when we calculated the uncertainty. We could have looked at it in centimeters, in which case it would have been 1/10 of a centimeter. So it would have been 0.9 centimeters. Okay. But the ruler in this case is precise to the nearest millimeter because that's the smallest notch or scale division on the ruler. Okay. So let's take a couple of examples. This is really what you want to be able to do. So Layla measures the radius of a circle, finds it to be 28 millimeters. What's the precision? Nearest millimeter, right? If it was point something, it'd be nearest 1/10 of a millimeter. If it was point something something, it'd be nearest 100. But because there's no decimal, the precision is to the nearest millimeter. So therefore, the uncertainty is 1 millimeter. The precision, divide 2, which is 0.5 millimeters. That's the uncertainty. Which means, and here's how you would write your final answer, it could be 0.5 millimeters above or 0.5 millimeters below. And then for the final answer, you're going to take the measurement that Layla got and add this to it. So your final answer is going to be 28 plus or minus 0.5 millimeters. Okay. The next one. Brendan measures his height, finds it to be 72.0 centimeters. So what's the precision? 1/10 of a centimeter, or 0.1 centimeters, or 1/10 of a centimeter. Either one of those is correct, but when we state the uncertainty, it's easier to use decimal. So how do I calculate the uncertainty? Well, I take the precision, 0.1, divide by 2, and that gives me 0.05 centimeters. Therefore, the uncertainty is plus or minus 0.05 centimeters. And then to state your final measure answer, you take the measurement that Brendan got, 72, don't forget the 0.0, plus or minus 0.05 centimeters. Okay. So those could be questions you could see. Now, uncertainty and accuracy, like I said, the true measurement can't be absolutely determined because no measuring device is perfect. Okay? But devices with greater precision will provide precise answers They could provide accurate answers, but they could also provide inaccurate answers. Because remember, like I said, you could have something that's very precise. If you measure it over and over again, you get pretty much the same number. But it may not be accurate. Okay? So what do we have to do to instruments when that happens? Well, the word is we have to calibrate it. Okay? And that means basically to adjust them. So, I mean, calibration is done all the time. I mean, I can think of like those home blood pressure where you can get your blood pressure, you can measure your blood pressure. A lot of times, like if you take your blood pressure, you know, you'll get the same sort of blood pressure over and over again, but it may not be related to the, or it may not be actually the true blood pressure because the machine isn't properly calibrated. So a lot of machines have to be calibrated. That's just the first example I think. Okay, because my blood pressure machine doesn't seem to be calibrated. Okay. So a 100-gram baseball is weighed 3 times on a very precise scale. The 3 weights are 84.523, 84.528 grams, and 84.531 grams. Would you say this is precise? Are the 3 measurements pretty close to each other? Yeah. I mean, it's not going to be perfectly precise, but I mean, it's 84.523. These two are only 0.005 apart. These two are only 0.003 apart, so that's pretty precise. Okay. So the scale is pretty precise. Because the 3 measurements are close to each other. 2 measurements are quite close to each other. What would you say about the accuracy? What's the true weight of the baseball? 100. What did we kept getting on our whatever device we were using? 84 point something. Would you say that's accurate? No. Not very accurate. Three measurements. Are quite lower than the true measure of 100 grams. And what would cause it to be inaccurate? Yeah, not calibrated properly. Or it's not calibrated. No, sorry, not calibrated properly. Okay. And the final example, science, physics. The accepted measurement for acceleration due to gravity on Earth is 9.8 meters per second squared. Abby completed an experiment designed to measure the acceleration due to gravity by dropping various objects and measuring the distance the objects fell and the time it took for them to fall. After she completed her calculations, she found a measurement of 9.5 meters per second squared, plus or minus 0.5 meters per second squared. Is the accepted value for gravity 9.8 within Abby's range of uncertainty? She got 9.5. What's the highest her measurement could be? 10. What's the lowest? Is 9.8 within that? Yes. So, is the accepted value? Yes. Because with uncertainty, Abby's results range from 9.5 minus 0.05 equals 9 meters per second squared, and 9.5 plus 0.5 equals 10 meters per second squared. And 9.8 meters per second squared falls in this range. That would be the explanation. But let's say Abby got 9.5 plus or minus 0.2. Would the accepted value fall within this range? No, because Abby's range is 9.5 minus 0.2, 9.3 meters per second squared to 9.5 plus 0.2, which is 9.7 meters per second squared. And 9.8 meters per second squared is outside this range. Okay. So just to sort of recap, okay, we talked about how to calculate uncertainty and then to write a measurement that includes uncertainty. And we also solved a couple of problems involving uncertainty. Okay, so the last thing that we'll do tomorrow is on tolerance, and I'll give you the assignment tomorrow because I have it ready to go. Okay.